So when we talk about equilibrium, we're talking about things when all the forces are in balance, which means if I asked you for the net force, what would the net force be? 0, right? Everything's balanced, so when you add everything all up, it should equal 0. Well, if the net force is 0, what should the acceleration be? Also 0. So a good example would be, a stapler on a desk. If a stapler is sitting on a desk, it's in balance, right? All the forces are 0, acceleration is 0. Most of the time when we talk about it, we do mean something that's not moving. However, it is possible for something to be moving and be in equilibrium. What's an example of that? Something that's moving but in a state of equilibrium. Sorry, say that louder. Say it a little bit louder. Oh, something, okay, the concept of inertia, objects in motion stay in motion. And so if the acceleration is 0, if something's in motion, moving at what kind of velocity? Constant velocity, then that would also be in a state of equilibrium. Good. So if you throw something in space away from gravity, it would continue moving, right, with no acceleration. Okay. We're going to talk about simpler cases, though. Let's start with the real simple case. What if I hang something by a rope? Okay, so if I hang Fufar by a rope like this, right? This is a state of equilibrium. Let's say he has a mass of 100. Okay, well, let's just kind of rush through this quickly. If I asked you for the FBD, we have, what do we have? Well, we have the weight coming down, and we have the tension going up. Weight going down, tension going up. Well, when we sum up our forces, it's just going to be tension minus weight equals ma. This is just the y direction. If it's just standing still, what's our acceleration? 0. Okay, which means the tension should equal the weight. Right, and hopefully that makes sense to you. If this is 100 newtons pulling down, how much weight force should pull up? 100 newtons should pull up, right? Okay, pretty easy. All right, what if we take 2 strings? Okay, so if I hang Fufar by 2 strings, like this, how did things change? Well, visually, hopefully you can see you have a tension and a tension, and a weight going down. So it should be 2t up, right? And weight going down, that'll equal 0. So what should be true about the tension? Should equal half the weight. Should make sense, okay? It's just kind of obvious almost, where if it's 100 pulling down, each string is going to have to pull up 50 and 50 going up. Okay? All right, so let's change it up a little bit. This time, instead of holding them straight up, I'm going to hold them at an angle. Okay, so how does this change things? What do you guys think? Do you think I'm going to have to pull with more tension or less tension if I'm holding them at an angle, or the same? So I heard the same and I heard more. No one thinks less? Oh, less too? All right, so why don't you, in your mind, think of which one it might be, okay? Think of the logic behind it for yourself at least. And we'll go ahead and solve it and then talk about the reasoning why. So let's draw this one out. So we're going to stick with 100. So if it was straight up and down, we know it'd be 50-50, right? 50-50 in each. So we're going to find out what is the tension. Let's go ahead and make this, say, 40 degrees. And we'll keep it simple. We'll make both angles the same, 40-40. And essentially, I'm going to ask you what's the tension in each. So let's call this T1, and let's call this T2. Okay, so our free body is pretty much the same. We have W coming down. We have tension going this time at an angle, and another tension going at an angle, T1 and T2. Okay, so what's the issue with these two? They're at angles, right? Just like the warm-up that you did, what do you do when you have things moving at angles? You find the components, right? So we're going to find the components of the two going up and across. So for example, this one right here, try to use colors. This one right here, part of the force is going up and part of the force is going to the left. So we could call this, say, T1x and this T1y. Likewise, the other string, part of the force is going up, part of the force is going to the right. So we can call this one T2x T2y. So when you try to visualize this, so you watch as I'm pulling this, like my right arm right here, it's pulling up and it's pulling to the left. This one on this side is pulling up and it's also pulling, or it's pulling the opposite way to the right. So that's what's going on with the two strings. Okay, so if I draw just a pure XY free body, we have the weight, and then we have this one which we said was T1x. We have this one which is T1y, T2x, T2y. All right, and so then the big question is, well, what are these? Can we find these? Well, we can't find them directly, but we can kind of work our way towards it. For example, if I gave you numbers, you probably would have no problem getting this. So for example, if I said tension 1 was 20 newtons, and I asked you to find T1x, how would you find T1x? 20 cosine 40. If I found this one, if I said this was 20 and asked you to find this, how would you find T1y? 20 sine of 40, right? So we're going to do that same concept, but we're just going to use variables. Instead of numbers, we're just going to use variables. So for example, I'm going to draw this. That's getting messy. Let's do this one here. So this is T1. So I could say this one coming up, this was what, 40? So this one, I'm just going to say this, let's do this one first, the T1x. This would be T1, and then this is the adjacent side. So we do cosine or sine? Cosine. So I'm just going to call that T1 cosine of 40. And the same thing on this side, except this is the opposite side. So we'll call this T1 sine of 40. Likewise for the T2, remember this was T2 at an angle. This was 40. So this T2x would be T2 cosine. And this one over here, T2y, would be T2 sine. Alright, so not that much different from what we did in the warm-up today with the problem, except we're just going to use variables here instead of numbers. Alright, and so that's our T1x or T1y. If you want to write these over here, you could. I'm just going to leave them like this, and then in our equation, I'll go ahead and substitute. So once we have our FBD, what's our next step? Set up our equation. So we have two dimensions, right? So once you have this picture, it should be pretty straightforward for you on how to proceed. So we have our T2x to the right. We have our T1x to the left, so we are going to subtract those. It's always equal to MA. Now equilibrium is actually easier than the problems we've been doing because what was A always going to be? It's always 0 for both sides. On the y side, we're going to have T1y plus T2y minus the weight equals MA, which is 0. Okay. So let's go ahead and just do our triangle. Let's fill in our triangle stuff here. Actually, what is this going to tell us? T2x is equal to T1x. So T2x, we already found here. That was T2 cosine. T1x, we found that right here. That was T1 cosine. So notice this is nice. What does that tell us about the two tensions? They're equal. Now you probably could have predicted this ahead of time, okay? This will always happen when the angles are the same. So because it's 40-40, the two tensions are going to be equal to each other. When they're not the same angle, you can't make that assumption. Okay, let's keep going on the y side. Ultimately, we're looking for the tension. Remember, we wanted to see how does it compare to the 50 from before. So T1y, we solved that triangle right here. That's T1 sine 40. T2y, we solved that right here. That's T2 sine 40. Minus w equals 0. I'm just going to go ahead and say that equals w. Again, the concept of this is the two upward forces should balance with the weight. These two are holding up the weight here. Well, notice we have two unknowns, T1 and T2. What can we do? Well, we found out that they're equal, right? So really, we don't have two unknowns. We only have one unknown since they're the same. So you could simply say, all right, this is going to become T1. Since T1 equals T2, we could simply call that T1. And then we have T1 sine plus T1 sine, which equals 2T1 sine. And I'm going to go ahead and substitute for the weight. That's 100. Okay, almost done. What's T1 then? 100 divided by 2 sine 40. Make sure you can plug it in. People always calculate this wrong.
77.79.
Make sure you can plug this in. People always make mistakes on this one. 77 point what?
79.
And let me just show you what people always do to do this wrong. They do this. 100 divided by 2 sine 40. Okay, what's wrong with this? So your calculator does order of operations here, so it'll go sine divided by 2 and then multiply by the sine. So if you're going to do it all at once, just make sure you parenthesize this. And make sure you're in degrees mode. Okay, 77.8. So what happened to the tension? Did it go up or go down? If it was straight up and down like this, right, what should the tension be in each? 50. So as we start increasing the angle, what happens to the tension? Increases. Good, it's going to increase. Why does it increase? When I'm going like this, all my force is straight up and down, right? So if this is 100 down, each chord's going to take 50, 50, 50. If I go like this, I'm not just pulling straight up and down. I'm pulling to the right and to the left, okay? So that overall tension's going to increase. I'm not pulling up, or I'm not pulling directly up, so it's going to get more and more and more.